The crew of Artemis II splashed down in the Pacific Ocean off the coast of San Diego on April 10, 2026. 4 astronauts, 10 days. The farthest any human beings had traveled from Earth in more than 50 years. And when the recovery teams pulled them from the water, blinking against the California sun, smiling in their orange survival suits, waving at the cameras, they looked more or less fine. But here is what the cameras did not show you. Here is what the handshakes and the press conferences and the triumphant highlight reels will never fully capture. On a cellular level, in their bone marrow, in the density of their vertebrae, in the expression of thousands of individual genes, in the calibration of their vestibular systems, and the tone of their cardiovascular walls. Those 4 people were measurably, quantifiably different from the 4 who had launched 10 days earlier. Not broken, not sick, but changed. The human body is an extraordinary machine, and when you take it somewhere it was never designed to go, it does exactly what evolution programmed it to do. It adapts, fast, ruthlessly, without asking permission. And sometimes those adaptations are the problem. Reed Wiseman, Victor Glover, Christina Koch, and Jeremy Hansen had just completed a circumlunar trajectory aboard the Orion spacecraft, swinging around the far side of the Moon and reaching a maximum distance of 252,756 miles from Earth. That number eclipsed the previous record set by the crew of Apollo 13 in April 1970, a record that had stood for over half a century and had been set, let us not forget, under circumstances of catastrophic crisis. The Artemis II crew broke it deliberately, methodically, as a proof of concept. They photographed over 7,000 images of the lunar surface. They watched the sun disappear behind the Moon from a vantage point no human eyes had ever occupied. They experienced 40 unbroken minutes on the far side of the Moon where the bulk of the lunar body itself blocked every signal from Earth. No radio contact, no telemetry, no reassuring voice from mission control. Complete and total isolation at 250,000 miles from home. They returned as heroes. But more importantly for the future of our species, they returned as data. This video is about that data. It is about what 10 days in deep space actually does to the human machine, and why those 10 days matter so much more than the mission duration might suggest. The moment everything changed. Let us go back to April 1st, 2026. The Space Launch System has just delivered Orion to orbit. The engines have cut off, the vibration has ceased, and for the first time in the careers of 3 of these 4 astronauts, Wiseman, Glover, and Hansen, there is no more up, there is no more down. There is only the soft, disorienting, perpetual float of microgravity. Christina Koch already knew this feeling. She had spent 328 days aboard the International Space Station between 2019 and 2020, setting a record for the longest single spaceflight by a woman. She had felt her face swell, her legs thin, her sinuses fill with the fluid that was no longer being pulled earthward by gravity. For her, this was a familiar, if still unsettling, transition. For the others, it was something new, something their bodies had never experienced in evolutionary history, something no human body was ever designed to handle. On Earth, approximately 2 liters of fluid pool in the lower body at any given moment. Gravity keeps it there, pulling it down toward the feet, the calves, the ankles, the way water settles at the bottom of a glass. It is so constant, so relentless, so utterly normal, that our cardiovascular architecture was built around it over hundreds of millions of years of vertebrate evolution. The heart pumps upward against gravity. The valves in the leg veins prevent backflow. The arteries in the lower body maintain higher pressure to overcome the gravitational column. Every single heartbeat is, in part, a fight against Earth's pull. Remove that pull, and the system does not fail. It just stops fighting. That 2 liters of fluid begins migrating upward almost immediately after orbital insertion. Within hours, the chest fills, the head fills, the face swells, the sinuses congest as if gripped by a ferocious head cold, and the legs, stripped of their fluid cargo, grow noticeably thinner. Astronauts have a darkly comic nickname for this phenomenon: puffy face, chicken legs. If you had compared a photograph of any Artemis 2 crew member taken on day 3 of the mission with their official NASA portrait from 6 months earlier, you would have thought they were unwell. The eyes narrower, the cheeks rounder, the jaw slightly softer. But they were not unwell. Their bodies were simply doing precisely what bodies do, adapting to the environment they were in. The problem is what those adaptations cost. The heart that shrinks. The cardiovascular system is one of evolution's most impressive engineering projects. Over hundreds of millions of years, vertebrate hearts have been refined into extraordinary pressure pumps, designed specifically to move blood vertically against the constant opposition of gravity. Your heart right now, as you read or watch this, is working against approximately 1 meter of gravitational head pressure, just to push blood from your chest to your brain. That is a non-trivial force. It shapes everything: the thickness of the ventricular walls, the calibration of the baroreceptors in the aortic arch, the resting tone of the peripheral vasculature. In microgravity, that opposition vanishes overnight. The heart, suddenly presented with a radically reduced workload, does what any efficient system does: it downsizes. The ventricular walls begin to thin. Cardiac output drops. The left ventricle, the main pumping chamber, loses mass. This is not pathology. It is optimization. A heart working without gravitational resistance does not need to be as powerful as a heart working with it, and the body, in its brutal pragmatism, does not maintain infrastructure it no longer needs. On a 10-day mission like Artemis 2, this cardiac remodeling is modest but measurable. Studies using echocardiography on returning ISS crews have documented ventricular mass reductions of up to 10% after 6-month missions. 10 days is not enough for dramatic structural change, but it is enough to begin the process. And crucially, it is enough to create a dangerous vulnerability at the end of the mission: the return to full gravity. Imagine spending 10 days gradually reducing your cardiovascular fitness, not through laziness, but through the physics of your environment. Then imagine being subjected to almost 4 times normal gravity during re-entry, with blood suddenly crashing back down toward your legs and feet, and a heart that has spent the last 10 days learning that it does not have to work very hard. That is the physiological reality of splashdown. It is not coincidence that specialized medical teams were waiting for the Artemis 2 crew on the USS John P. Murtha. It is not theater. The risk of orthostatic intolerance, the inability to maintain blood pressure when returning to an upright posture, is real and serious. Astronauts returning from extended missions have been known to faint simply from standing up. After 10 days in microgravity, the cardiovascular system requires time, support, and careful management to recondition itself to Earth. The crew wore specially designed compression garments beneath their pressure suits during the re-entry phase, a practical engineering solution to a biological problem that no amount of training can fully prevent. These garments help maintain venous return and prevent blood from pooling so precipitously in the lower extremities during the transition back to gravitational loading. They work, they help. But they are, in essence, a workaround for the fact that we are taking machines designed for one gravitational environment and operating them in another. The skeleton that dissolves. Most people think of bone as inert, a framework, dead structural material like the steel girders of a building. This is one of the most consequential misconceptions in popular biology. Bone is alive. Bone is dynamic. Bone is in a state of perpetual demolition and reconstruction. governed by two rival cell populations engaged in a never-ending negotiation with your environment. Osteoclasts are the demolition crew. They dissolve old bone tissue, releasing calcium and phosphorus back into the bloodstream. Osteoblasts are the construction crew. They lay down new bone matrix, mineralizing it into hard, load-bearing structure. On Earth, the mechanical forces of gravity, the compression of your skeleton every time you stand, walk, climb stairs, carry groceries, provide a constant signal that stimulates osteoblast activity. Your bones, in effect, are told by gravity, "Be strong, because I need you to be strong." Remove gravity, and that signal disappears. The demolition crew keeps working. The construction crew slows down. Nobody told them to stop demolishing. They are responding to the same biological signals they always have. But nobody told them to keep building either, because the signal that justified the construction, the gravitational load, is gone. The result is a net loss of bone mineral density that proceeds at approximately 1 to 1.5% per month in weight-bearing regions of the skeleton: the hips, the lumbar spine, the femur. For context, postmenopausal women experiencing osteoporosis typically lose bone at roughly 1 to 2% per year. Astronauts on long-duration missions can lose the equivalent of a year's worth of osteoporotic bone loss every 30 days. The Artemis II crew had a flywheel exercise device aboard Orion, a compact resistance trainer weighing about 13 kilograms, roughly the size of a large carry-on bag. Its purpose was to provide some mechanical loading to the skeleton, simulated rowing, squats, deadlifts using bungee cord resistance in a spacecraft smaller than most studio apartments. It helped. 2 hours of daily exercise is the standard recommendation for ISS crews, and it does meaningfully slow the bone loss process. But it cannot prevent it entirely, because you cannot fully replicate the complex multi-directional mechanical loading of normal gravity-based locomotion with a flywheel trainer in a space capsule. For a 10-day mission, the bone loss is not catastrophic. But studies on mice exposed to radiation levels comparable to solar particle events have shown measurable functional bone loss within 72 hours of exposure. And the Artemis II crew was dealing with both microgravity and radiation simultaneously, a combination that potentiates cellular damage in ways that are still not fully understood. Which brings us to the thing that made Artemis II genuinely, historically different from every human spaceflight of the past 5 decades. Beyond the shield, radiation in deep space. The International Space Station orbits at an altitude of approximately 400 kilometers. It is inside Earth's magnetosphere, the invisible magnetic cocoon generated by our planet's iron core, which deflects the vast majority of high-energy charged particles coming from the Sun and from the broader galaxy. The ISS is not perfectly protected. Its occupants receive radiation doses significantly higher than those experienced on Earth's surface. But it has a shield, a big, planet-sized shield. The Artemis II crew left that shield behind. On their trajectory from Earth to the Moon and back, they pass through the Van Allen radiation belts, 2 toroidal regions of magnetically trapped particles extending from roughly 1,000 to 60,000 kilometers above Earth's surface. During both the outbound and return legs of the mission, the crew transited these belts, moving through concentrations of high-energy electrons and protons moving at enormous velocities. Beyond the belts, in the true deep space between Earth and Moon, they were exposed to the full unattenuated spectrum of cosmic radiation. Galactic cosmic rays, GCRs, are among the most energetically extreme forms of radiation in the known universe. They are atomic nuclei, stripped of their electrons and accelerated to near-relativistic velocities by supernovae, neutron star collisions, and other cataclysmic astrophysical events. They are not like the X-rays or gamma rays that dominate discussions of medical radiation exposure. They are macroscopic objects moving at nearly the speed of light, and they punch through matter the way a rifle round punches through paper. Iron ions, heavy nuclei from GCRs, account for approximately 13% of cosmic ray dose by ionizing effectiveness. A single iron ion passing through living tissue does not merely ionize molecules as it passes. It creates a cylindrical track of dense ionization damage, a literal scar carved through the DNA and cellular machinery of every cell in its path. The cell may die immediately from this insult, or, and this is worse, it may survive. It may survive with broken chromosomes, misrepaired double-strand breaks, frame-shifted genes. It may continue dividing, passing those errors to daughter cells, accumulating mutations that will not manifest clinically for years or decades. The Orion spacecraft carried 6 radiation dosimeters distributed throughout the crew cabin, and each astronaut wore a personal dosimeter throughout the mission. These were not merely for monitoring, they were the early warning system for solar particle events, which can spike radiation exposure by orders of magnitude within minutes. In the event of a significant solar flare during the mission, the alarm would have sounded and the crew would have retreated to the most heavily shielded section of the capsule, sheltering in place until the particle flux subsided. As it happened, the sun was cooperative. No major flares, no coronal mass ejections directed at the spacecraft. The total radiation dose received by the Artemis II crew over their 10 days in deep space was, by the standards of a professional astronaut's career lifetime limit, relatively modest, roughly equivalent to the dose from a single chest CT scan. Manageable, expected, within acceptable parameters for a short mission. But acceptable for a short mission is a very different calculation from acceptable for a 3-year Mars transit. And that is precisely the point. The Avatar experiment, reading biology from the inside. NASA did not send the Artemis II crew to the moon and back without trying to extract every possible biological datum from the experience. Among the dozens of experiments carried aboard Orion, one stands out for its conceptual elegance and its slightly unsettling implications about how we think about human biology in space. It was called the Avatar experiment. The full name, Vascular Tissue Challenge, astronaut virtual analogs for tracking radiation. Here is what they did. Before the mission, scientists at the Weiss Institute at Harvard University collected platelet samples from Reed Wiseman, Victor Glover, and Jeremy Hansen. From those platelets, they derived induced pluripotent stem cells, essentially stem cells that can be coaxed into becoming almost any cell type in the body. Those stem cells were then differentiated into bone marrow cells and cultured on organ-on-a-chip devices, microfluidic platforms roughly the size of a USB thumb drive, engineered to mimic the architecture and functional physiology of living human bone marrow. Blood vessels, hematopoietic niches, the structural scaffolding of the tissue that produces every red blood cell, white blood cell, and platelet in your body. These chips, physical proxies for the bone marrow of 3 of the 4 crew members, flew aboard Orion, mounted to the interior wall of the cabin. They experienced the same trajectory, the same microgravity, the same radiation environment. Everything the astronauts experienced, their cellular proxies experienced simultaneously. Meanwhile, identical chips remained in the laboratory at Harvard, serving as Earth-based controls under ambient conditions. Bone marrow was not chosen by accident. It is one of the most radiation-sensitive tissues in the human body. It is also, arguably, one of the most important. Damage it, and you compromise immune function, red blood cell production, and platelet generation simultaneously. Severe radiation damage to bone marrow, as experienced by victims of nuclear accidents or high-dose therapeutic radiation, produces a syndrome that is life-threatening precisely because it undermines the body's ability to fight infection and maintain circulatory integrity. For a 10-day mission, nobody expected the Avatar chips to show anything as dramatic as radiation sickness. The dose was too low. But the experiment was not designed to detect gross pathology. It was designed to detect whispers, molecular signatures, the subtle shifts in gene expression that precede, by months or years, any clinically apparent consequence. Using single-cell RNA sequencing upon the chip's return to Earth, researchers planned to map how the expression of thousands of individual genes had changed across thousands of individual cells. Comparing the deep space samples to the Earth-bound controls and to the blood samples drawn from the crew members themselves before and after the flight. The question being asked was not, did this 10-day mission harm the crew? The question was, what does this 10-day mission tell us about what a 3-year mission might do? The Avatar experiment was a molecular time machine designed to let us read the future of long-duration spaceflight in the biology of a short one. Dr. Stephen Platz, NASA's chief scientist for human research, has described the principal hazards of deep space exploration using the acronym RIDGE: radiation, isolation, distance from Earth, gravity fields, and hostile environments. The Avatar experiment was designed to probe the R. The other letters had their own investigators. The muscles that forget how to stand bone loss gets the attention. It is dramatic, quantifiable, directly analogous to a recognized disease process on Earth. But the muscle atrophy that occurs in microgravity may actually be more immediately debilitating upon return, because it affects function in real time, in ways that are visible and felt. Human musculature, like human bone, is calibrated to the gravitational environment in which it evolved. The postural muscles, the deep spinal erectors, the hip stabilizers, the calf muscles, and the quadriceps are perpetually active on Earth, making the thousands of tiny adjustments required to keep a bipedal primate upright against gravitational pull. These are the muscles that fatigue when you stand in line too long. They are the muscles that cause your back to ache after a day of walking on uneven terrain. They are doing work constantly that you never consciously notice because you have been doing it without thought since you learned to walk. In microgravity, they stop. There is no posture to maintain in weightlessness. The spinal column decompresses, actually lengthening the body by up to 2 inches over the first few days of a mission, as the intervertebral discs, no longer compressed by the weight of the torso, absorb fluid and expand. The back muscles that would normally fight this expansion simply disengage. There is nothing to fight against, and unused muscle fiber, like unused bone, is dismantled by the body's relentless efficiency. Research data suggests that astronauts can lose up to 20% of muscle mass during a spaceflight lasting 5 to 11 days, a range that includes the entire duration of the Artemis II mission. The Orion spacecraft's flywheel trainer was specifically engineered to mitigate this, a resistance-based system allowing compound movements including simulated deadlifts, squats, and rowing. Daily exercise sessions were mandatory. They worked, partially, but exercising in a vehicle smaller than most people's living rooms, in microgravity, with 3 colleagues sharing the same constrained space, is not equivalent to a structured terrestrial strength training program. The physics are different, the loading patterns are different, the metabolic environment is different, and there is a subtler change that is less often discussed, the alteration in muscle fiber type composition. Human skeletal muscle is not uniform. It contains a spectrum of fiber types, ranging from slow-twitch oxidative fibers, optimized for endurance and sustained postural work, to fast-twitch glycolytic fibers, optimized for explosive power and rapid movement. On Earth, the postural demands of bipedal locomotion maintain a relatively high proportion of slow-twitch fibers in the weight-bearing muscles of the legs and trunk. In microgravity, without any postural demands to sustain, these slow-twitch fibers begin converting to fast-twitch fibers, effectively restructuring the muscle's fundamental character at the myosin heavy chain level. The body is literally rewiring its hardware for an environment where bursts of movement matter, and sustained postural endurance does not. This is adaptive brilliance from an evolutionary perspective. It is an operational nightmare from the perspective of returning astronauts who need to walk out of a spacecraft on their own. Eyes under pressure. The SANS syndrome. Since the early 2000s, NASA flight surgeons have been increasingly concerned about a phenomenon observed in a substantial proportion of long-duration spaceflight crews. About a third of astronauts returning from long missions to the ISS show structural changes in their eyes, changes that can persist for months to years after their return to Earth. The condition is known as spaceflight-associated neuroocular syndrome, or SANS. The mechanism connects directly back to the fluid shift we discussed earlier. When gravity is removed, the 2 liters of fluid that migrate upward do not stop at the chest. They continue into the head, increasing intracranial pressure. This pressure is transmitted through the cerebrospinal fluid to the optic nerve sheath, the fluid-filled tube surrounding the optic nerve as it exits the skull. Elevated pressure in this sheath creates a progressive, sustained force on the posterior globe of the eye. The eyeball, over weeks or months, gradually flattens. The optic nerve head can develop swelling, papilledema. The retina can develop folds. The functional consequence: astronauts who had perfect vision before their mission find themselves unable to read without glasses by the end of it. Their near vision has deteriorated, typically into farsightedness, as the flattened posterior globe shifts the focal point of the lens system. In the most severe cases, some of these changes have proven difficult or impossible to fully reverse after return to Earth. For a 10-day mission like Artemis II, full SANS syndrome was not expected. The structural remodeling that produces it requires weeks to months of sustained elevated intracranial pressure. But the fluid shift begins within hours of launch. Intracranial pressure was almost certainly elevated throughout the mission. And the groundwork for structural change, the cellular environment, the tissue stress, the sustained pressure on the optic nerve sheaths, was actively developing throughout all 10 days. Astronauts on the Artemis II crew wore compression garments specifically designed to resist this fluid shift on the return leg of the mission, attempting to pull some of that fluid back toward the lower body before the full weight of Earth's gravity imposed itself. This is an imperfect countermeasure. It helps. It is not a solution. The brain that was never consulted. There is one more system we have not discussed yet, and it may be the most disorienting of all: the vestibular system. The network of fluid-filled semicircular canals and otolithic organs in your inner ear that tells your brain where you are in space, which way is down, and how you are moving. The system that, in combination with proprioceptive feedback from your joints and muscles and visual cues from your eyes, gives you the fundamental experience of having a stable orientation in the world. In microgravity, the vestibular system is not broken, but it is profoundly confused. The otolithic organs, small calcium carbonate crystals resting on sensory hair cells, normally tell your brain how gravity is pulling on them, which indicates which way is down. In microgravity, they float. They provide ambiguous, contradictory signals. The brain, which has been interpreting vestibular input as a gravity vector for the entirety of the person's life, cannot immediately make sense of this new input. Approximately 50 to 70% of astronauts experience space motion sickness in the first days of a mission: nausea, vomiting, headache, spatial disorientation. This is the vestibular system's protest against an environment it was not designed for. Most astronauts adapt within 48 to 72 hours as the brain recalibrates its interpretation of vestibular signals for the new environment. Christina Koch, with her 328 days of experience, adapted rapidly. Her colleagues, for whom this was a first flight, endured the transition. The return to Earth reverses this process. The vestibular system, having spent 10 days in microgravity, has recalibrated for that environment. When gravity returns during re-entry and splashdown, the signals from the otolithic organs suddenly become huge and overwhelming, the opposite extreme from the silence of weightlessness. The brain must recalibrate again under conditions of physical stress and cardiovascular strain. Some returning astronauts experience transient vertigo lasting hours to days. Some require assistance simply walking in a straight line. The world, which should feel normal again, feels wrong. This is not a minor inconvenience. When you are exiting a spacecraft in the open ocean, with wave action adding additional vestibular noise, with a cardiovascular system struggling to maintain blood pressure, and with muscles that have spent 10 days in disuse, the inability to maintain stable balance is a genuine safety hazard. Every breath, a variable. There is a detail about life aboard Orion that receives almost no attention in the media coverage of space missions, and it is more significant than it might seem. The atmospheric composition is not quite the same as Earth air. Spacecraft atmospheres are carefully controlled environments, maintained at sea level pressure with approximately Earth normal oxygen partial pressure. But carbon dioxide levels are slightly higher than what we are accustomed to on the surface, because managing CO2 in a small, sealed volume with multiple respiring humans is technically challenging. Even small elevations in ambient CO2, at levels far below those that would cause acute toxicity, have measurable effects on cognition, headache frequency, and sleep quality. Approximately 70% of astronauts report headaches in space. This is not a trivial statistic. Headaches in a pressurized spacecraft are not like headaches at home. You cannot open a window, take a walk in fresh air, or retreat to a quiet room. The headache is present in every moment, in the same 9 cubic meter volume, sharing space with 3 colleagues and the constant background hum of the life support systems. And when you combine slightly elevated CO2 with elevated intracranial pressure from fluid shift and disrupted sleep architecture, you have a headache that is neurologically reinforced from multiple directions simultaneously. Sleep, aboard Orion, is itself a challenge. The spacecraft has no dedicated sleeping quarters. The crew sleep in their seats, with minimal isolation from the ambient light and noise of the cabin systems. Actigraphy devices worn on the wrists of each crew member tracked their sleep quality and duration throughout the mission, providing data that will inform the design of sleeping arrangements for future deep space vehicles. The data was expected to show significant disruption: fragmented sleep, shortened REM phases, elevated nighttime activity. Sleep deprivation compounds every other biological stress. A cognitively impaired crew member is a safety risk. An emotionally dysregulated crew member, trapped in a vehicle smaller than a studio apartment with 3 colleagues for 10 days, is a social risk. The psychological dimension of deep space exploration is not separate from the physiological dimension. It is inseparable from it. The immune system under siege. The human immune system is, in many ways, the most complex regulatory network in our bodies. It is also, as decades of spaceflight medicine have demonstrated, profoundly sensitive to the physiological stressors of spaceflight. Multiple mechanisms contribute to spaceflight-associated immune dysregulation. The stress hormones, cortisol and epinephrine, are chronically elevated in the early phases of a mission, suppressing immune cell activity. The redistribution of bodily fluids alters the lymphatic drainage patterns that immune cells depend on for communication. Radiation directly damages immune cells, particularly the lymphocytes that are critical to adaptive immunity. And the disruption of circadian rhythms, near total in a spacecraft with no natural day-night cycle during portions of the mission, further dysregulates the immune system's diurnal activity patterns. The practical consequence: astronauts are more susceptible to infection in space. Wounds heal more slowly. And perhaps most alarmingly, viruses that have been latent in the body for years, members of the herpes virus family, including the varicella-zoster virus, responsible for chickenpox and shingles, and the Epstein-Barr virus, can reactivate. To probe this phenomenon, the Artemis II crew collected saliva samples throughout the mission onto specialized absorbent paper strips, a method chosen because Orion carried no refrigeration equipment for biological specimens. These samples will be analyzed after the mission for evidence of herpes virus reactivation, the presence of viral particles in saliva indicating that dormant viruses have re-emerged under the immune pressure of spaceflight. Studies on ISS crews have found reactivation of multiple herpes virus strains in a significant proportion of astronauts. The question for the Artemis II data is whether 10 days in deep space, with its additional radiation exposure beyond the magnetosphere, produces measurable immune dysregulation even in such a short window. The answer may matter a great deal for mission planning. A crew member with a reactivated varicella-zoster infection is not immediately incapacitated, but the same logic that makes herpes virus reactivation a useful indicator also makes it a warning sign. If the immune system is showing this level of strain on a 10-day mission, what happens during a 3-year Mars transit? The psychological architecture of isolation. In January 2026, just months before the Artemis II launch, NASA astronaut Michael Fring experienced a transient neurological event aboard the International Space Station. For approximately 20 minutes, he lost the ability to speak. Flight surgeons ultimately cleared him of a cardiac event, but the incident was sufficiently alarming that Fring was returned to Earth on an expedited schedule, one of the rarest medical evacuations in the history of the space station. Now imagine that event occurring on the far side of the Moon. During the 40 minutes that the Artemis II crew spent on the lunar far side, cut off from all radio contact with Earth by the intervening mass of the Moon itself, there was no communication, no real-time medical consultation, no option to abort the mission and return within a clinically meaningful time frame. If a crew member had suffered a cardiac event, a stroke, a severe allergic reaction, a traumatic injury, there would have been only the crew's onboard medical kit and each other. The closest hospital was 238,855 miles away. This is not a theoretical concern. It is a design constraint. It is the reason that crew selection for deep space missions involves psychological screening as rigorous as the physiological selection criteria. The ability to function effectively under conditions of acute medical stress, in complete isolation, with no external assistance available, is not a personality trait. It is a trainable skill set, and it requires specific, targeted preparation. Jeremy Hansen, the Canadian Space Agency astronaut flying on Artemis II, spent a week in total isolation in a cave complex deep beneath the Italian Alps in the months before his mission. A psychological conditioning program designed to simulate the cognitive and emotional experience of isolation, sensory deprivation, and confined space living. He had to manage resource constraints, communication delays, and the psychological weight of knowing that the surface was inaccessible. The experience was specifically designed to stress test his psychological architecture in controlled conditions. But no cave prepares you for the radiation environment of deep space. No cave prepares you for the moment your body starts doing things you did not ask it to do. No cave prepares you for the headache that will not go away, or the disorientation that makes the walls of your tiny spacecraft feel like they are tilting, or the knowledge that you are farther from another human being than any person alive. Christina Koch knew this. She had spent 328 days on the ISS, and she had faced the accumulating psychological weight of long-duration spaceflight in a way her crewmates had not. She had learned the importance of structure, routine, communication, and small rituals of normalcy, the things that keep a human mind functional in an environment designed to destabilize it. The behavioral monitoring study aboard Artemis II, tracking crew teamwork dynamics, decision quality, interpersonal interaction patterns, and emotional regulation, was collecting data not because NASA did not trust the crew, but because every data point from a real deep space mission is irreplaceable for designing the psychological support systems of future ones. The crews going to Mars will be 6 people in a can the size of a house for 3 years. Understanding how group dynamics evolve in deep space, with communication delays that make real-time conversation with Earth impossible, with no option of evacuation, with the constant background stress of an environment actively hostile to human physiology, is not a soft science. It is mission-critical engineering. The cascade of consequences. Every biological change we have discussed, the fluid shift, the cardiac remodeling, the bone demineralization, the muscle atrophy, the vestibular disruption, the immune suppression, the radiation exposure, the sleep disruption, the psychological stress, does not occur in isolation. These systems interact. They potentiate each other. They create cascades. Elevated intracranial pressure impairs sleep quality. Sleep impairment elevates cortisol. Elevated cortisol suppresses immune function and accelerates bone resorption. Immune suppression increases susceptibility to viral reactivation and infection. Radiation exposure damages both immune cells and bone marrow directly. Bone marrow damage compromises immune cell production. Muscle atrophy reduces the mechanical loading that bones require to maintain density. Reduced bone density increases fracture risk under the cardiovascular stress of re-entry. And over all of this hangs the 24-minute communication delay to Mars. At maximum orbital separation, a radio signal from Earth takes approximately 24 minutes to reach Mars. A response takes another 24 minutes to return. In a medical emergency, a crew member on the Martian surface, or in transit between the planets, could wait nearly an hour for a reply to an urgent medical query. In that hour, depending on the nature of the emergency, the clinical situation could be entirely transformed. The crew would need to be medically self-sufficient in ways that no human crew has ever been required to be in the history of spaceflight. The Artemis program is building toward this. The Gateway Lunar Space Station, a small orbital outpost to be assembled in the mid-2020s in a near rectilinear halo orbit around the Moon, will serve as a staging point for lunar surface missions and as a testbed for the life support, radiation protection, and medical systems that Mars missions will require. The data from Artemis II, from the Avatar biochips, from the saliva immunology samples, from the actigraphy sleep data, from the crew's blood panels and bone density scans and cardiovascular assessments, feeds directly into the engineering decisions for Gateway, for the lunar surface habitat, and eventually for the deep space transit vehicle that will carry 6 people to Mars. 10 days of data. But 10 days of data from a real mission, under real conditions, involving real human bodies at real distances from home. That is something no simulation, no Antarctic isolation study, no undersea Aquarius habitat experiment can fully replicate. The biology of space is not equivalent to the biology of any analogous extreme environment on Earth. The radiation is different. The microgravity is different. The combination is different. The food that tastes like nothing. There is an aspect of the Artemis II mission that does not appear in the technical papers and the mission briefings, but that any astronaut who has experienced it will tell you matters enormously for the quality of daily life in orbit. Everything tastes wrong. The nasal congestion caused by the cephalad fluid shift, the stuffing up of the sinuses as fluid floods upward in the absence of gravity, suppresses olfactory function dramatically, and human taste is approximately 80% olfaction. Eating in microgravity, with congested sinuses and no gravity to help food move naturally through the digestive tract, produces a gustatory experience roughly equivalent to eating with a severe cold while inverted. Things that should be flavorful taste muted. Textures that should be appealing feel wrong. The relationship between you and your food, one of the most fundamental sources of pleasure and psychological comfort available to humans, becomes estranged. The Artemis II mission menu addressed this with characteristic pragmatism. 58 tortillas, the standard bread substitute in microgravity, because they produce no crumbs that can float into electronic equipment, as conventional bread does. Smoked brisket, vegetable quiche, spicy green beans, 5 different hot sauces, maple syrup, Nutella. The hot sauce was not a luxury, it was a medical necessity. When your entire palate is suppressed by sinus congestion, the chemical burn of capsaicin, which activates pain receptors, not taste receptors, and is therefore unaffected by olfactory suppression, is one of the few sensations that fully penetrates the numbness. Astronauts systematically reach for the most intensely flavored, most chemically aggressive foods available to them in space, not from indulgence, but from genuine physiological need. The crew rehydrated their freeze-dried meals using Orion's water dispenser and heated them in a specially designed meal, warmer the size of a small briefcase. Eating in microgravity requires careful management. Crumbs and liquid droplets that drift away become hazards for electronic equipment and respiratory pathways. Each meal was, in a small way, an exercise in controlled chaos. Food secured, liquids managed, crumbs intercepted, the entire process accomplished in a vehicle with 3 other people, in the lingering aftermath of nausea and vestibular disorientation, with a persistent headache, while performing mission-critical cognitive tasks. The cumulative psychological weight of 100 small discomforts, of food that tastes wrong, sleep that is inadequate, a body that behaves strangely, a habitat that is cramped and noisy and vibrating, is not trivial. These are not dramatic, acute threats. They are the kind of grinding, daily erosion of comfort and normalcy that over weeks or months can degrade cognitive function, damage interpersonal relationships, and compromise mission effectiveness. Human factors engineers at NASA spend enormous resources on these seemingly minor quality-of-life issues, precisely because they are not minor. The astronaut who cannot sleep, cannot taste food, cannot stop their head from aching, and cannot find a quiet moment to think, in a vehicle smaller than a large SUV for months at a time, is a mission risk. The numbers behind 10 days. Let us be very precise about what we are talking about, because the numbers make it real in a way that general description cannot. The Artemis II crew returned to Earth with approximately 1 to 2% reduction in bone mineral density in their femoral necks and lumbar vertebrae, based on projections from comparable short-duration missions. Not catastrophic. Recoverable with weight-bearing exercise over the following weeks, but measurable and a warning of what a 30, 60, or 180-day mission would produce at an accelerated rate. Their cardiac left ventricular mass was likely reduced by several percent, modest but measurable by echocardiography. Their cardiovascular response to orthostatic challenge, the ability to maintain blood pressure when standing up, was impaired, requiring medical support during recovery operations. Their plasma volume, the liquid component of blood, had decreased because the body reduces blood volume when less is needed to maintain central venous pressure in microgravity. This hemoconcentration affects everything from red blood cell count to medication dosing. Their immune profiles showed patterns consistent with spaceflight-associated immune dysregulation, with evidence expected from the saliva samples of herpes virus reactivation in at least some crew members. Their cortical bone density, assessed at weight-bearing sites, had begun the first measurable steps of demineralization. The bone marrow avatar chips, en route to the Weiss Institute laboratory for single-cell RNA sequencing, carried a molecular record of what 10 days of deep space radiation did to hematopoietic stem cells. All of this from 10 days, 1 decade of days, 240 hours, 14,400 minutes of departure from the gravitational and electromagnetic environment that produced every cell in every body that has ever lived. Now multiply that by 900. That is approximately how many days a Mars transit will require. The reckoning ahead. NASA's trajectory is clear. Artemis 3, scheduled for the late 2020s, will land humans on the lunar surface for the first time since Apollo 17 in December 1972. Artemis 4 will deliver a crew to the Gateway Lunar Space Station for an extended stay. And beyond that, in a timeline that shifts with budget cycles and technical readiness, but remains the foundational goal of the agency's human exploration program, Mars. A Mars mission at current propulsion technology involves roughly 6 to 9 months of transit to reach the planet, 18 months on the surface waiting for the planetary alignment that allows a return trajectory, and another 6 to 9 months of transit home. 3 years, give or take. 3 years of microgravity in transit, 1/3 Earth gravity on the surface, and no magnetosphere anywhere along the route. The bone loss projection alone is sobering. At 1% per month, a 6-month transit produces 6% reduction in femoral neck density, bringing some crew members into the clinical range for osteopenia before they even set foot on the Martian surface. On Mars, at 38% of Earth gravity, the mechanical loading from walking and working is significantly less than on Earth, meaning the recovery rate on the surface will be slower than it would be in terrestrial rehabilitation. And the return transit begins that demineralization process again before the surface stay has allowed full recovery. The radiation calculation is more complex because it depends on solar activity, mission architecture, and the effectiveness of shielding. But NASA's current estimates for a Mars transit suggest a total mission radiation dose of approximately 0.66 sievert for astronauts using existing spacecraft shielding, roughly equivalent to the career radiation limit currently set for ISS astronauts, all used in a single 3-year mission. The risk of radiation-induced cancer, cognitive impairment from galactic cosmic ray exposure to neural tissue, and potential hematopoietic failure is not theoretical. It is a known, quantified risk that every Mars mission planner must account for. The Avatar experiment was designed to help close this gap. If researchers can identify the molecular signature of early GCR-induced hematopoietic stress from a 10-day sample, they can begin developing countermeasures, pharmacological agents that protect bone marrow cells, dietary interventions that enhance cellular repair, shielding designs that attenuate the most damaging heavy ion components of the GCR spectrum. They can begin personalizing those countermeasures to individual astronaut biology, because the Avatar chips are derived from specific crew members' cells and will reflect individual variation in radiation response. Dr. Platts and his colleagues at the Human Research Program are not working on the assumption that these problems are insoluble. The history of medicine is the history of problems that seemed insoluble until they were not. Scurvy was insoluble until someone noticed that citrus prevented it. Anemia in long-distance runners was insoluble until someone understood iron metabolism. Bone loss in postmenopausal women was a normal consequence of aging until bisphosphonate drugs demonstrated that it could be pharmacologically arrested. The biological barriers to Mars are real. They are serious. They are not yet solved, but they are no longer unknown. And that is what missions like Artemis 2 are for. What came home in 4 bodies. On April 10, 2026, at approximately 3:09 p.m. Pacific Time, the Orion capsule struck the surface of the Pacific Ocean at nearly 40,000 kilometers per hour and began the controlled deceleration of re-entry. The heat shield, the component that had generated the most anxiety among NASA engineers after cracking on the uncrewed Artemis 1 mission, and which had undergone extensive redesign and testing in the intervening years, performed flawlessly. Temperatures on the exterior surface reached over 2,760 degrees Celsius. The crew, 6 minutes inside a radio blackout caused by the plasma sheath surrounding the decelerating capsule, experienced sustained G-forces approaching 4 times normal gravity. 4 times normal gravity. On bodies that had been trained by 10 days of weightlessness to require less of the cardiovascular system than at any point since these people had been born. on hearts that had been downsizing, on vascular trees that had been relaxing, on vestibular systems that had recalibrated for an environment with no gravity at all. The parachutes deployed, the G-forces eased, the capsule descended into the Pacific. The recovery teams deployed from the USS John P. Murtha. The hatches opened, and 4 people who had been to the far side of the moon blinked in the California sunlight and were carefully, gently helped out of the vehicle, because getting out on their own, quickly and unassisted, was not something their bodies were currently capable of doing without real risk of injury. They spent the first hours aboard the recovery ship, undergoing the first of many weeks of medical examination. Blood draws, echocardiograms, vestibular assessments, ophthalmological exams, bone density measurements, cognitive performance batteries. The data collection that had begun months before launch and would continue for years after it. In the weeks ahead, they would relearn standing, relearn walking without assistance, relearn the proprioceptive landscape of a world where their feet push against a floor that pushes back. Their hearts would begin rebuilding the mass they had lost. Their bones would begin remineralizing under the stimulus of bearing weight again. Their vestibular systems would recalibrate for a world where down is a fixed direction. Their immune systems would stabilize as cortisol levels returned to baseline and circadian rhythms reestablish themselves. Their plasma volumes would normalize. Their muscle fiber type ratios would begin, slowly, shifting back toward the postural slow twitch composition required for efficient bipedal locomotion. The body is extraordinarily good at recovering. It is one of the things that makes us a viable candidate for space exploration at all. But it is not infinitely good at recovering. And each successive mission, each additional accumulated dose of radiation, each further month of microgravity-induced bone loss, each new instance of stress-induced immune dysregulation compounds the previous ones. The career radiation limits that NASA sets for its astronauts are not arbitrary bureaucratic thresholds. They are the mathematical boundary between acceptable and unacceptable lifetime cancer risk. When you push against those limits with a 3-year Mars mission, the margin for subsequent errors disappears. The only draft that matters. The Artemis II mission did not answer the question of whether human beings can go to Mars and come home healthy. It was not designed to answer that question. It was designed to provide the first irreplaceable fragment of data from which an answer might eventually be constructed. The Avatar biochips are in a Harvard laboratory, being sequenced. The saliva immunology samples are being analyzed. The actigraphy data is being integrated with the cognitive performance assessments and the crew questionnaires and the blood panels into a comprehensive portrait of what 10 days in deep space did to 4 specific human beings in 2026. That portrait will be compared to the portraits painted by every previous long-duration mission, every ISS crew member who has ever donated their biology to science, every rodent study and cell culture experiment and ground-based simulation that has been used to model what spaceflight does to living systems. And from all of that data, this sprawling, incomplete, constantly expanding archive of what happens when you take biology into physics it was not designed for, researchers will construct the roadmap for human Mars exploration. It will not be a complete roadmap. It will be a first draft, a rough sketch, a document full of blank spaces and provisional answers and questions that open into further questions. But a first draft written in real biology, from real people, at real distances from home, under the real conditions of the deep space environment that awaits every future crew, is immeasurably more valuable than any simulation. It is the beginning of a map for all the steps that come after. We sent 4 people to the moon, nearly. We brought them back. We measured what the journey cost their bodies, down to the level of individual gene expression in individual cells. And in that measurement, however incomplete, however preliminary, however surrounded by uncertainty and unknowns, we are, perhaps, beginning to understand what it will take to go further. If you found this video valuable, please take a second to hit the like button. It genuinely helps this kind of in-depth science content reach more people. And if you want to follow the ongoing story of human space exploration, including what the Artemis program discovers next about the biology of deep space, subscribe so you do not miss what comes next. The data from Artemis 2 is just starting to come in. The story is only beginning.